So in this lesson, we're going to be going through turning points and stationary points. Now, we've looked at turning points and stationary points before. We did so in quadratics, and we did it again in cubics. So these are no new concepts. We're just adding another method to finding turning points to our repertoire. So we've already got a few techniques. We're going to learn a couple more. The first thing we need to look at before we do max and minimums is the slope at any given point on a graph. So from the previous lessons, we should be pretty used to the idea that the derivative gives us a slope at a point. So you can see my ruler there. That would be the slope at about x equals 2. So when x equals 2, the tangent line there gives the slope. We can see the slope when about x equals, negative 1, sorry. When x equals 0, I've lost my ruler. When x equals 1, we're over here. When x equals 2, we're up here. Okay, so the derivative gives us the slope at a point. Okay, so what we're going to do first is we're going to find the slope at different points. So I've got a pretty basic example here. It's just y equals x squared. So a normal positive quadratic. And we're going to find the slope at a couple of different points. So y equals gives me the value of y at point x. I don't want the value of y, I want the slope. Okay, so I'm going to find dy over dx. I'm going to use rule, which I encourage you to do unless you are told to do first principles. So my slope at any given point is 2 times whatever x is. So if you're asked a question such as, what is the slope when x is 2? The slope is 4. Okay, so for every 1 it goes over, it goes 4 up. That looks about right. Okay, 1 over 4 up. So it gives us the slope at point 2. If we wanted to find the slope when x is negative 1, okay, again, we're just using dy over dx. Okay, so for every 1 we go across, we go down 2. Right, so we're trying to find the slope at a given point. And you'll notice with quadratics, you're going to have a negative slope, negative slope, negative slope, negative slope, no slope, positive, positive, positive. And that's the lead into what we're going to be mainly looking at today is how to find those turning points. Okay, but you also need to be able to find the slope at any given point. Okay? So slope is just dy over dx or f dash x, and that will give you the slope at any point. So stationary points are the points in the graph where the gradient is 0. Okay, so if we get our ruler out here, on this linear equation, there is no point where my ruler is flat, where the gradient is 0. Okay, on this quadratic, we can see it goes down, slopes around, and there's a point there where there is no slope, where the gradient is 0 and it's completely flat. Okay, then it turns and it keeps going. Same with the cubic, goes up, turns, there's a point where the gradient is 0 and then it continues on its way. This quartic here, negative, flattens out, goes up, flattens out, turns around, flattens out, goes up. Okay, so we can actually use the derivative to find the turning points, and that happens when the slope is 0. Okay, when it's not going up, it's not going down, it's just stationary. I've just got a question there, how many stationary points are there on these graphs? The linear one, there is none. The first one, there is 1 stationary point where the gradient is flat, okay, and that's a minimum. Here, there's 1 point where the gradient is flat, that's a stationary point of inflection. Remember that from cubics. Here we've got a couple of points where the gradient's flat. There's one there, there's one there, and there's another one there. Okay, so from this, when we differentiate, if we differentiate a cubic, like we just did, we get an answer that is linear. Okay, we're going to have one answer. Same with this one here. But this one over here, we're actually going to get 3 answers. So when we get our derivative, we're going to have an x cubed term in there, okay? And we're going to have 3 answers from it. So just be aware with this that there's more than one answer because there might be more than one turning point, and that depends on the type of the graph. Now, when I say type of the graph or type of the stationary point, there are 3 different types that we're going to be looking at in this course. So there is a local maximum, a local minimum, and a stationary point of inflection. We have seen all of these things before, remember. So local minimums go negative, in my little drawings here, negative, they turn, they go stationary, and then they go positive. So B would be a minimum, okay? Negative, flat, positive. A maximum goes positive, flat, negative, okay? Just like in the graph. So there's a picture there. A would be a local maximum. A stationary point of inflection, they go up, flat, up, or down, flat, down. Okay, they don't change direction at all. So C would be a stationary point of inflection. Now, in this course, there's a specific way that you need to prove what type it is. And sometimes this can be a little like ticking the boxes because if you graph it, you can see very, very quickly if it's going to be a maximum or a minimum. But there's a certain way you need to prove it. So I'm going to show you how to do that. So on this one, I've worked out what the stationary point is, and it occurs at -3, -7, and I'll show you how to find that on the next part. Okay, but I just want to show you first how to prove what type it is. So what we're going to do is we're going to look at the x value of the stationary point, and we're going to put it in this table over here, and I'm going to pop it in the middle. Okay, so when x is -3, I want to know what dy over dx is, or the slope is. Okay, I've already got that here, dy over dx. I've already done it for you. So we're just going to plug in 2 times -3 plus 6. Okay, -6 plus 6. The slope is 0, which means it's flat. Okay. Now this table, as I said, is a way that you have to prove what type it is. There'll be questions that specifically ask you to prove or justify, and this is what they're talking about. So what I'm going to do is I'm going to pick a point to the left and a point to the right, and I'm going to have a look at the slope on both those sides. You can just go one more, so you could go -4 and -2. You can go a couple more, it doesn't really matter. Don't stray too far from the point, but which point you choose is not really important. So I'm going to just go -4 and -2. Okay, one either side. So the slope when x is -4 is -2. Okay, it's a negative. It's going down like that. I'm going to do it again with a point to the right side. Okay, on the right side, it's +2. The slope is going up. Now, from that table, you can see that down, flat, up is our local minimum. Okay, and it kind of draws it for you. If you think about that, it's a quadratic. It goes down, it hits a minimum, and it goes back up. That's a minimum that it reaches. Okay, so those tables we need to use for kind of everything that we work through. If they ask you to justify the type or determine their nature, this is what we're talking about. So from all this, these are the notes that you really need. So if dy over dx or f dash x, so the derivative is 0, there is a stationary point there. That is, there is a maximum, there is a minimum, or there is a stationary point of inflection. Okay, down here, I've spelled derivative wrong. By finding the derivative function and setting it equal to 0, we can find those stationary points. Okay, so I've put a step-by-step here if you're a step-by-step kind of person. So if you want to find a maximum, minimum, or any kind of stationary point, You're going to find the derivative, first of all. You're going to set the derivative equal to 0. I've spelled it wrong again, but differently. You're then going to solve for x, and then you're going to sub x into the original function to find y. Okay, do not sub it back into the derivative. The derivative does not tell you what the y is. It tells you what the slope is. So that's a common mistake that people make. Make sure you put it back into the original function. So what I'm going to do now is go through a couple of examples, finding the stationary points of different functions and also justifying their type. So I'll go through, I think I've got 4 or 5 here, and when you get the hang of it, just stop the video and go on with the worksheet. Okay, you don't have to watch them all, maybe watch the first one and then it's up to you. So we're going to find the stationary points of the following functions. So we're going to use our little steps here. We're going to find the derivative, set it equal to 0, solve for x, and then sub x into the original to find y. So step 1, find the derivative. Unless it asks you to do it with first principles, rule all the way. Unless you've got a lot of time off your hands, which I doubt any of you do. So we're going to drop the 2 down, negative 4x plus 12. Okay, so that gives us the slope at any given point. When the slope is 0, that's where our turning points occur. And then we just have to solve for x to get the x coordinate of the turning point. Okay, so if we think about this, this is a negative quadratic. It's going to look like that-ish. I'll move it over a little bit so it makes a bit more sense. So the turning point has a coordinate of 3 something. Okay, we need an x and a y for a coordinate. So I'm going to sub this back into the original function to find y. Okay, have I already done this? I have 27. So that point there is 327. So we've got a stationary point at 327. Now, in some questions that will be enough. In others, they will ask you to justify the type, and we're going to do that too. So I've got my little table here. I've got enough room for the labels and 3 separate points. So my labels are the x-coordinate, the slope, and graph. Okay, you can use x, dy over dx, and picture. It doesn't really matter. You cannot use labels at all, as long as the table follows the general format. So x, we've got the one in the middle, that's when x is 3, and I'm going to go 1 either side, so 2 and 4. Okay, I'm going to plug 3 into dy over dx. Now we've just solved this for 0, so if you get anything other than 0 at this point, go back and fix it, because otherwise the whole thing's going to go pear-shaped. So that's negative 12. That's 12 if I'd wrote it right, and that's 0. So that's flat. Okay, I'm going to do the same with 2. So negative 8 plus 12 is 4. So it's positive. And I'm going to do the same again with 4. That's negative. Okay, you can see there it's drawn us a little picture, and that is a maximum. Please do not follow my setting out on this one. That's pretty good on the left-hand side there. The rest of it, try and keep it a bit neater. That went all over the show, and I'm sorry. So we need x and y, and we also justified our answer there. So this next one, we've actually got a cubic function. So if you think about what a cubic function, in particular what a negative cubic function looks like, we're going to be like that. We're going to have 2 points where the gradient is 0. So we're going to end up with a maximum and a minimum. Okay, so I'll need 2 of those tables, but I'll do that in a minute. So we're looking for a stationary point. The first thing we're going to do is find the derivative. By rule, unless they specify otherwise. and then we're going to set that derivative equal to 0. We're going to solve for x. And here is a really common place that people make mistakes. If you square root a number, it could be a positive or a negative. For example, 1 times 1 equals 1. So therefore, the square root of 1 is 1. But also, negative 1 times negative 1 is positive 1. So the square root of 1 is also negative 1. So you have 2 answers here. Okay, do not just do 1 because you won't be able to find the other point. You won't be able to find the other maximum or minimum. Okay, so as soon as you square root a number in this, make sure you do positive and negative. So you can write it like that, or you can write it plus or minus 1. Either one's fine, but yeah, if you square root, you've got 2 answers. Make sure you use them both. So now I have got my coordinates. So actually, I'll leave that back on there. So I've got one point that occurs at -1, and I've got another point that occurs at 1. So I'm going to find the y coordinates for both those points. And this little graph here is a good idea. You all kind of know what quadratics and cubics and quartics look like. If you can just do a rough sketch, it'll help you think about this process and check your answers as you go. So let's plug these values for x in so we can find the y values. So we're going to find f of 1. Remember, back into the original function. So that would be 6. Okay, so that's a point there. And with -1, -1 cubed is -1. That would give us 2. Okay, so I have stationary points at, that would help if I did this, at -1, 2 and 1, 6. So 2 points, and now I'm going to find out whether they are maximums or minimums. Now let me just copy this table. That's better. Okay, so x, f dash x, or slope and shape. So we're going to do one of these for each. So in my first point, I've got -1, and I'm going to go 1 either side, so -2 and 0. And for my other one, I'm going to put my 1 in there and go 1 either side as well. So let me see if I'll coordinate this a bit. Let's do that one's there. And let's find out what type it is. So I'm going to plug these into f dash x of -1, and I'm first of all going to check that this equals 0, and if it doesn't, I'm going to go back and redo this problem. So -1 squared plus 3. The -1 squared is 1, -3 times 1 is -3, plus 3 is 0. Good. Okay, so this one is flat. I'm then going to do it again once I've checked that it is correct. I'm going to go with -2. So -2 squared is 4, -12 plus 3 is -9. So that's a -1. And f dash x of 0. Missed my equals. 0 squared is 0, 0, 3. Okay, so that one there, the green one, that is a minimum. What have I done? My graph, my original graph is upside down. It didn't make sense for a minute. Okay, so it would be like that. So my -1 is a minimum. Okay, and I've proved that using the table. So just make sure if you do those little scribbles with the graph that they're up the right way, because I completely missed the negative out of that. So let's try and figure out the other point. We might go red for this one. So I'm going to do that all again, but I'm going to use these other points. So I've got f dash x, and I'm going to use 1 to start with to check that everything's okay. -3 plus 3 is indeed 0. So I have found that x coordinate. All right. This is going to be 3, so that's positive. -9. So that's going down, so negative. Okay, so you might notice something here with this one. If you're squaring the x's, it doesn't matter if they're positive or negative, they're the same number. So there's a little shortcut there if you can spot it, but if you're not confident, just pop it in every single time. So I've got a minimum in the first one, and I've got a maximum with that second point. Okay, so up to here, with those 2 points, we'll answer most of those questions on your sheet. The ones that ask you to justify, so say here, state what type of stationary point it is, you will have to do that table. Now, I might make this our last example. And if you've done your worksheets from the last unit, you will know that with these brackets that are squared, there are 2 different ways of doing it. So I'm only going to do it the one way. You should have seen both of them in the last one. So if I'm finding stationary points, I am first of all finding the derivative. So if I've got y, change it into the y of the x. I'm going to drop the power first. And then I'm going to expand. Okay. I feel I've done something wrong there. I have 6. Okay, so that is my derivative. I'm then going to set it equal to 0. Got the sinking feeling. I've picked a fraction for the last one and I'm not happy about it. So x equals 6 over 4, which is -3 on 2. Thankfully, this is a quadratic, so we'll only have to find 1 point, which means we'll only have to do 1 lot of fractions. So we're going to sub that back into the original. So -3 on 2, this is to find the y coordinate. And I'm going to do what I tell you not to do, and I'm going to put it in the calculator. And y is 1/2. So you should, with time, be able to sit down and do that. I'm not going to take that time doing it in the video because I will bore you greatly. But we've got the y there and we've got the x. So we've got a stationary point at -3 over 2 and 1/2. Okay, now this is where the table does come in handy. As far as drawing a rough sketch of that, most people would struggle. It is just a positive quadratic, so we're probably looking at a minimum, but the table will help prove that. So let's get our table here. Oh. Well. Okay, there is an easy way and a hard way to do this. So we know that this is going to be 0 because otherwise we've done everything wrong. And we want to pick points either side of this. Now this here is -1.5. You can pick -1 3/4, but you're going to have to do more fractions. So -2 and -1 would be easy. -2 and 0 are going to be even easier. Okay, so you want to find whatever makes life easier for you. Okay, so I'm going to try with -2 we've got 4, -2 plus 6, -8 plus 6, -2. So we've got a negative slope there. I'm going to do it again with 0, which is 6, which is a positive. So this here, this stationary point, is a minimum. Okay, and I can see that from my drawing. All right, so you can pick whatever points you want for this table. I wouldn't stray more than 2 or 3 away from the point, because what might happen is if you've got, say, a cubic, this might be one point here, and if you go over 2, you might have turned around again, and it's not going to give you the negative that you need. It's going to instead give you a positive. So just 1 either side is good, 2 is fine. Don't go any more than 2 or 3. Okay, but that's it. So stationary points and justifying types. So have fun with that sheet. It starts off pretty easy, kind of just subbing in and evaluating, gets a bit harder, and then there's some worded problems at the end when you're feeling more confident, and then after that you should be pretty right to do quite a few of those assignment questions as well. So good luck.